Hello everyone, in this video I'm going to show you how we can plot the phase Bode plot for this given transfer function. Alright, we know h of j omega is equal to h of s when s is equal to j omega. Alright, we also know that h of j omega is a complex valued function. With that, I can write h of j omega in polar coordinates like this. I can represent it in polar coordinates. So with that, I have h of j omega, magnitude of this one, multiplied by e to the j angle or phase of h of j omega. Now, the job is to plot this one, this angle magnitude of h of j omega in the logarithmic scale versus omega, and this one with the units of degrees versus omega. In the Bode plots, I'm going to plot these two. Next, I'm going to write h of s in the format as the multiplication of three different functions. So I'm going to write h of s is equal to 1000 multiplied by 1 over s plus 1 multiplied by 1 over s plus 10. I want to write each one of these terms in the format of transfer functions in the categories that we saw for the Bode plots. So this one, this term, this function, and these functions match the transfer functions with one single real pole. So that's that. This transfer function in the category of single real pole looks like this one. 1 over 1 plus s over omega naught. All right, so I'm going to again continue and write it so that it matches, the terms match that general h of s. That 1000 is just a constant number, so I'm going to write it as 1000 multiplied by 1 plus s divided by 1 multiplied by 1 divided by, now I'm going to write, actually in the numerator, I'm going to have 1 over 10. So this is 1 over 10 divided by 1 plus s over 10. Now this one, I'm going to further simplify it and write it as 100. So this is 1000 divided by 1/10. It's going to give me 100 multiplied by 1 over 1 plus s over 1 multiplied by 1 over 1 plus s over 10. Now I have these functions, this one and this one, in the similar format as this our general h of s for the category of transfer function with single real pole. All right, and next the job is to write h of j omega using in this for each one of these transfer functions multiplied by each other, and that's going to give me 100 divided by 1 plus j omega divided by 1 multiplied by 1 over 1 plus j omega divided by 10. All right, so omega naught for this function is 1 and omega naught for this function is equal to 10. And this is this omega naught that I'm talking about. So next, the magnitude of h of j omega is going to be equal to magnitude of this function multiplied by magnitude of this function multiplied by the magnitude of this function, and the phase of h of j omega is going to be equal to phase of this function plus phase of this function plus phase of this function. I'm going to show you next, I'm going to show you why this is the case. Next, I'm going to represent each one of these terms in the polar coordinate with their magnitude and their angle. So 100 is equal to 100 multiplied by e to the j multiplied by 0. The angle, this is a positive real number, so the magnitude of this number is 100 and the angle is 0. And for 1 over 1 plus j omega divided by 1, this is going, I can write it as the magnitude of this complex function, j omega divided by 1 multiplied by e to the j angle of this function. 1 over 1 plus j omega 1. I want to show you why. To find the angle of h of j omega, you can add the angle, calculate the angle of each one of these functions separately and then add them up. This is the proof for that. All right. So the other one also, 1 over 1 plus j omega divided by 10 is the magnitude of this function, 1 over j divided by 10 multiplied by e to the j angle of 1 over 1 plus j omega divided by 10. All right, so next I need to multiply all of them to get h of j omega. So with that I have h of j omega equals to 100. So I'm going to write it in this form. Instead of writing 100, I'm going to represent it in the polar coordinates. So control copy, and then this is paste, then multiplied by this function, which I wrote it as multiplication of in the polar coordinates. So that's that, and I'm going to multiply it by this. And next, let me pull everything up a little. Actually, I can make it smaller. Okay, next I'm going to multiply it, and this one also should get smaller. Next I'm going to multiply it by this term, which is another way of showing the same function, 1 over 1 plus j omega over 10. Copy and then paste. So these two terms are the same. Look, this is the same thing. Okay, I just wrote each one of those three functions in the polar format. All right, so with that, let me delete this and rearrange the location of these three functions multiplied by each other. So I'm going to bring this close to this one because I want the magnitude multiplication to be at one side and these these complex functions multiplied by each other at one side. So with that, now you can compare this function. We knew that h of j omega is equal to magnitude of h of j omega multiplied by the angle of h of j omega. So if you compare these two with each other, you're gonna see that this angle of h of j, this magnitude of h of j omega is equal to multiplication of these three functions, and the angle of h of j omega is equal to this one plus this one plus this one. Just a side note, look, e to the j theta 1 multiplied by e to the j theta 2 multiplied by e to the j theta 3 equals to e to the j theta 1 plus theta 2 plus theta 3. Okay, because of that, the angle of h of j omega, or this function, equals to the angle of this function plus the angle of this function plus 0. All right. Next, I'm going to show you how you can draw the angle of h of j omega, or the phase Bode plot. All right, so far we know that the angle of h of j omega is equal to, this is the phase of h of j omega, is equal to angle of this function, 1 over 1 plus j omega divided by 1 plus angle of this function, 1 over 1 plus j omega over 10. And then plus 0 degrees, and it's like 0, so you can even discard it. All right, so we want to plot this function, the angle of 1 over 1 plus j omega over 1 separately, and then the other one, and then we are going to add them to get the complete phase plot. So let me copy this one. Let's plot this first. So I'm plotting the angle of h of j omega. This is my phase Bode plot, and then I'm going to label the y-axis. This is phase in degrees, and this is my omega. Okay, so we are going to, this is my omega naught for this function, and we saw that to draw the phase Bode plot for a transfer function with single real pole, we need to label omega naught, first find omega naught, label it. So this is my omega naught 1, and then label 1/10 of omega naught, which is this one, and 10 times omega naught, which is this one. All right, so for omega values less than 1/10 of omega naught, the angle is 0 degrees, the angle of this function. This is 0 degrees. For omega values greater than 10 times omega naught, the angle is negative 90 degrees. So for all these omega values, the angle is negative 90 degrees. When omega is equal to omega naught, we saw that the angle is negative 45 degrees. And the last part of the job is to connect these two line segments such that the third line segment goes through the point of omega naught and negative 45 degrees. So it goes through this one. All right, so this is the phase graph for this function. Next, I'm going to draw the phase graph for the other part of the for the second function. All right, so the other one was I want to find the angle of this function, 1 plus j omega divided by 10. All right, so and this is the omega naught value here. We are plotting the phase in degrees. Okay, so that's my omega, and then I'm going to label the omega naught value. This is 10, and then 10 times that omega naught value and 1/10 of it. For omega values less than 1/10 of omega naught, the angle is going to be 0, so it's here. For omega values greater than 10 times omega naught, the angle is going to be negative 90. It's going to go through negative 45 degrees when omega is equal to omega naught. Right, so the last part of the job is to connect them connect two line segments such that that the third one goes through the point of negative 45 degrees for omega naught. Right, the last part of the job is to add these two phase graphs linearly. So because I have, look at here, I know that the angle of h of j omega is equal to summation of the angle of the first function and the second one. So let me copy it and then come here. So I'm drawing the complete phase function. I'm going to add them on overlay these functions. So this is the first one, copy, and I'm going to paste it here. It was for 10, 1 and 100, right? So the other one was for this one, and then I'm going to copy it. All right, so located at, this is the second one, I believe. Yes. Okay, why don't I change the color of these two so that I know these are not the actual graphs. These are our guides to draw the phase of h of j omega, the graph of the phase of h of j omega. So with that, I'm going to change the color of these to perhaps gray, this one, and this one to something like let's see, lighter blue, perhaps. Maybe you can't see it, so maybe pink. Okay, so the job is to add these. All right, I'm also going to add some guide lines so that I can keep track of how I am adding them. So with that, let me add a guide line, a different color, perhaps this color. Okay, so for anything less than omega equals to 0.1, the angle is 0. So see, these two lines are at 0 degrees. So if I add them, the angle is going to be 0. So this is my line of 0. For anything, now moving this one away, or actually I can maybe copy it. For anything between omega values between 0.1 and 1 in this range here, the angle of the first one, this is 0, and this one changes. It's a line function, so I'm adding all of these numbers on the y-axis by 0. That means I'm going to have the same function. So with that, let me draw the same line here. This is part of my, actually, I should have used this one. So this is my line there. Next, moving on, let me copy and create another guideline. All right, so in here it's also easier to find it because the angle of the first one is negative 90 degrees. The angle of the second one is also negative 90 degrees. So these two lines are negative 90 plus negative. Each one of them is negative 90 degrees. So if you add them to each other, the answer is going to be negative 180 degrees. So that's going to be, oh, that is going to be this line. Okay. Next, another easy point. So let me copy. I can see that in here, in this range, this part is a constant number, negative 90 degrees. Now I have a line, equation of line in here. If I add these two together, I only need to add negative 90 degrees to this line. So I need to pull it down by negative 90 degrees. So if I do that, I'm going to have this line, but then actually, let me draw this line in this segment, but I need to bring it down to, oh, didn't work. So I'm gonna draw this line. Next, I'm gonna show it to you. Let me show you. Okay, so this is the line. This is the same line, this one. Brought down or pulled down by negative 90 degrees, or by pulled down by plus 90 degrees. So I'm adding negative 90 degrees, negative 90 to that line. All right, so that's my line. The next job is to find it in here. So I only need to connect this point to this point. That's going to give me the equation of that line. All right, so let's connect them, and that's going to give us our complete phase graph for this function. And let me duplicate this page and remove all of the guiding lines, and then that's going to give us a complete graph. Okay, this is a duplicate of that page. I'm removing all of the guidelines. This is going to go away. So that's the phase of h of j omega, or phase graph, phase of h of j omega in degrees. All right, and that should be my omega. All right, so that's the phase graph, phase Bode plot for this h of j omega, or for the given transfer function. Thank you for watching.